Now the video will focus on the rates topic, and rates is a very popular question, and in the past 2 to 3 questions have come up on rates because this topic tests you on graph, Arrhenius, on rate graphs, on rate calculations. So it's very heavily dependent on mathematical skills, but also there are 2 practicals we do for rates, practical 3 and practical 7. So that's why it's a very important topic. It's a short topic, but in terms of testing, it's a long topic. So I would say anything from 20 to 30 marks worth of questions can be on rates. Now, and because rates comes in with topic 2, with paper 2, and paper 2 involves organic chemistry as well. So if we look here, the rate of hydrolysis of bromoalkanes is investigated. Normally we do this as a practical in class. The boiling tube has a cross drawn on it, very similar to practical 3, the disappearing cross method. An aqueous solution of silver nitrate is added to RBR. Straight away you're looking for an AgBr precipitate, a cream precipitate here. Why does the cross become invisible? Visible because a precipitate of silver bromide forms. So precipitate forms. The volume and concentration are used to at each temperature is kept constant. State one other variable that could be kept constant to ensure the investigation is fair. Here you could say start the timer at the same point of addition, view the cross from the same distance. You could say same level of swirling here, so that could be another important one to do. A typical question now is, this is Arrhenius. So this just gives me the opportunity to talk about Arrhenius here. Now with Arrhenius you will be given this formula. So K is your rate constant. A is known as Arrhenius constant or a constant or pre-exponential constant. E is this letter E on your calculator. Depending on which calculator you use, I use a Casio one. It's one with looks like that, and on top of that you've got EX in orange, and that means natural log. EA is activation energy, R is gas constant, T is temperature in Kelvin. So now that you can write in a linear form, written like what it's circled in the question. Now you've got to learn both. So you've got to learn this equation. They're not going to give you this equation, and you've got to learn that you can make this into a linear form. The opposite or the inverse of exponential here is natural log. So if you natural log K, natural log A minus EA over RT. Now the purpose of this video is not to explain to you how to use a calculator. That at this level you should be comfortable in using. So the question is asking you to fill in this gap here. So be very careful here. You've got to convert temperature into Kelvin, and then you've got to do one of that, and that comes to 3.08 times 10 to the minus 3. The question is asking you to plot a graph of temperature, natural log K against 1 over T. You are given the axis, the y-axis, so you need to plot the x-axis, and I would say, depending on how you plot the graph, you need to go from 2.9 times 10 to the minus 3 to 3.2. So you got to go from 2.9 times 10 to the minus 3 to 3.2 times 10 to the minus 3. using the equation, the axes there. Again, these are mathematical skills which you need to be able to plot. You should get something like this, a straight line that practically is going to go something like that. Now, because the question is asking you to work out EA, once you plot the graph, EA is basically the gradient of the line is minus, sorry, the EA is minus gradient times 8.31. Now, how do you work out the gradient? The gradient should be worked out as two extreme points. Draw a dotted line, a triangle, to show how to work out the gradient. So the way I work out the gradient is like this. I will say do gradient is dy over dx. So the best way to do this is dy over dx is your gradient. So minus, so this distance here, so 2.38 minus 0.84 divided by 2.90 times 10 to the minus 3 minus 3.2 times 10 to the minus 3. That's my gradient. Gradient is dy over dx, so the extreme points. And that comes to, let me quickly work this out. And that comes to minus 107,333 times that by 8.31. So times by 8.31, and you get a gradient of minus 89194, which is minus 89.194 kilojoules per mole. Remember, it's EA is minus gradient times 8.31. So minus EA and minus gradient becomes positive. So the value for EA is going to be positive 89.2 kilojoules per mole. And that is how you would do an Arrhenius graph. Now, I haven't actually plotted it properly just to save time, but that's how you would be plotting this graph. Next one is this one, which is saying correct mechanism, meaning rate determining step. Your mechanism has to have the following in, which is correct. Okay, now the correct one is the one where you will have, it's one of these. Okay, the correct ones, because the rate determining step is the slowest one. The reason why it can't be C is because in the C, this first step is fast, whereas in B, if you look at B, the first step is slow because it contains BrCH2, which is the species present in the rate equation. So that would be the right answer. And then that's organic, which we can look at a later time. Now with question 2 is basically practical 7. Now there are two practical 7, 7a, 7b. One is where you are monitoring a gas by a continuous method. In this method, hydrogen peroxide reacts with iodide in the presence of sulfuric acid. You produce iodine, and then to detect iodine you need starch. So the experiment is done 5 times in the presence of thiosulfate and starch. That's thiosulfate and starch. The reactant concentrations are varied. After all thiosulfate has reacted, iodine produced reacts with starch to produce blue-black, and that will be the color change observed, and you will stop the timer at that time. Now look very carefully then. In this experiment, you've got hydrogen peroxide, iodide, and H plus in that respect. And starch is also added, and you're recording the time it takes for the reaction mixture to turn blue. So the amount of thiosulfate is the same in each experiment to allow the order of reaction with respect to each reactant to be calculated. What factors or what are the three control variables? Here you're going to control temperature, the amount or volume of starch, and you can have the third factor could be the total volume of reaction mixture is the same. So these are the three factors you would be controlling. Now, deduce the order of reaction with respect to each reactant. Okay, so we need to know with respect to each. The best way to do this is if you look at experiments 1 and 2, I minus is constant, H plus is constant, hydrogen peroxide is doubled, and the time taken for the reaction mixture halves, which means the rate doubles. So with respect to hydrogen peroxide, it's first order. If we look at these experiments 3 and 4, let me change the color here to blue. That's H2O2 is constant, H plus is constant, I minus doubles, that halves, so it's first order with respect to I minus as well, because the rate doubles also. Now what about H plus then? Well, if we look at this experiment, 4 and 5, hydrogen peroxide is constant, I minus is constant, H plus doubles, no change, so it's a zero order with respect to that. In other words, your rate equation here, let me write it here, is going to be K, H2O2 and I minus. That's your rate equation. Okay, and then you can do your explanation, determine the units of your, so if your rate is, it's that, then your units for K is rate. Now rate is mole per dm cubed per second over your concentration. Your concentrations will cancel with H peroxide and you will be left with that on the bottom. So the your units, mole to minus 1 dm cubed per second. So those are your units there. Next, in each experiment, 1 cubic centimeters of 1 times 10 to the minus 3 sodium thiosulfate solution is used to react with iodine. Total volume of the mixture is given in experiment 3. Calculate the initial rate of the production of that. So you have to work out the amount of thiosulfate, which is 1 times 10 to the minus 3 over the volume, which comes to 10 to the minus 6. And then you would say the amount of iodine is half of that, which is 0.5 times 10 to the minus 6. At this stage, don't worry about that on that. And then you will say that the concentration then will be moles times volume, so that will come to 1.25 times 10 to the minus 5, and then you just work out the concentration of iodine, which will be the moles of divided by total volume over 1,000. Okay, uncertainty, not going to go over this again. G says that the 5 experiments are repeated with the same stopwatch and same concentrations. Suggest and explain how the method can be changed to decrease the percentage uncertainty. Well, increase the time, use greater concentration or amount of thiosulfate so the color changes over a long period of time, and that will reduce uncertainty. Okay, next one is this is the standard one. So sketch a graph to show how how at constant temperature the concentration of bromine changes. It's going to change. Oops, it shouldn't go back up. Something like that. Okay, so it shouldn't go back up. That's a standard one. And if you have a concentration times time graph, to work out initial rate, you just need to draw a gradient at 0, something like that, a tangent, sorry, and then you just work out the gradient of that line for this, and that will help you to work out the concentration of that. We've done a similar question to this before, but to work out this concentration here, you know your rate equation, which is given there. So the first thing is work out K from rearranging using experiment 1 data, and then use the K value to rearrange the equation for hydroxide. I'm not going to do the calculation for you, but I'm just getting you to do that on that. Okay. Again, if you look at this question in front of you now, it says the rate of reaction between calcium carbonate and hydrochloric acid is investigated using a continuous method. The core practical you did was between magnesium and HCl. Same procedure. They've plotted the graph for you. And why do you leave the flask? It says choose why a loose cotton wool is placed instead of leaving the gas open. So that's going to prevent any of the solution to splash out, and it can allow the gas to escape. Because if you were to put a bung inside, the gas would build up, and then the bung can explode out, or the conical flask could break as such. Okay, and using this graph, you can again work out your initial rate by placing a tangent or drawing a tangent line about there. Okay, and that will help you to work out the initial rate. Another question I want to do with you, because there's a lot of variety of these questions, so my advice is to just to do as many of the past paper questions as you can, is again Arrhenius equation question. So same type of question, you just plot a graph. The one I want to do is this one here with this one. Okay, so this one I want to look at with you as a final question for today. So this question is Arrhenius equation type calculation, and what you have to do here is to do a calculation. The question says at temperature T the rate constant is given, and for a chemical reaction the relationship between rate constant and temperature T is shown. For the decomposition, you're given EA, you're given A, and you have to work out T. So what I would do now is I would convert this equation like this. And the other thing I will do is I will rearrange like this. Take the minus term across like that. And then T equals EA over R times natural log of A minus natural log of K. Okay, and now let's do our calculation. Well, EA is 34.5 thousand or times 1,000 joules because that's in kilojoules. R is 8.31, and natural log of A minus natural log of K I'm going to work out separate. So I'm going to do natural log, then 1 to the power of 12. So I'm going to do natural log 1 to the power of 12 minus, and then in brackets, minus open brackets natural log of 2.48 to the power of 8 close brackets, and that gives me a figure of 8.302. So I'm going to times 8.302. So you got 34.5 times 1,000. Divide that by 8.31 times 8.302, and that gives me an answer of 500.01, so 500 Kelvin. So in there I did 2.48 times 10 to the 8. So note, I rearranged the equation and then worked out that separately. Okay, and lastly, Boltzmann distribution at low temperature, at high temperature, must start at the origin, that's high temperature, label the axes, energy, activation energy, and the number of molecules with energy here. And at higher temperature, this is the additional number of particles that have energy above activation energy. And then that hopefully